It's 3 a.m. A single, unvalidated API endpoint accepts a malformed payload. Within minutes, a multi-gigabyte database is silently siphoned out to an unknown server. If your API is live on the internet, it is already being mapped. Automated scripts run continuous sweeps across the web, probing for open ports and weak validation logic. Relying on a single login page to protect your system is a brittle strategy. Modern architecture relies on defense in depth, a gauntlet of overlapping security layers designed to trap threats at multiple stages. In cybersecurity, the math is brutally asymmetrical. An attacker only has to find one tiny crack in the armor to get through. Your system has to perform flawlessly 100% of the time. Securing a .NET API requires deliberately engineering an environment where the failure of one defense mechanism immediately triggers the next. The first line of defense is transit encryption. By forcing HTTPS and SSL/TLS, data becomes entirely illegible to anyone trying to intercept it while it physically travels across network nodes. Next is CORS, a browser-level security feature. As we can see in this diagram, a browser's pre-flight check acts as a strict bouncer, physically deflecting data packets if an unauthorized domain tries to request resources from your API. But a single configuration error compromises this entirely. If developers pair an allow any origin wildcard with allowed credentials, that barrier drops. The system is instantly exposed to cross-site request forgery attacks. The fix in C# requires absolute precision. You must use explicit with origins policies to lock down the exact scheme, host, and port permitted to communicate with your server. Yet HTTPS and CORS are passive. They stop casual spoofing and browser-based tricks, but they do nothing if a determined attacker bypasses the browser and fires requests directly at your infrastructure. That introduces volumetric attacks. Botnets can simply crush your server's memory and CPU with a massive swarm of brute force requests. To survive this, you need an API gateway and rate limiting. Notice how the funnel mechanism in this schematic works. The gateway intercepts an overwhelming flood of client requests, compressing it into a manageable flow before reaching your application logic. You could use a fixed window algorithm to cap request per minute, but a token bucket approach handles sudden traffic bursts much better. It constantly fills a bucket with digital tokens. Every incoming request consumes a token, and if empty, the request is instantly dropped. Looking at this C# configuration in .NET 8, we add the token bucket limiter. By explicitly defining the token limit and a replenishment period, we dictate exactly how much traffic can pass through the funnel. Rate limiting will keep your server online during a flood, but it doesn't care who is sending the traffic. To separate legitimate users from actual threats, we have to verify identity. Identity verification breaks down into two distinct phases. Authentication determines exactly who you really are, while authorization determines exactly what you are allowed to do. Authentication frequently relies on JSON web tokens. The server issues a signed stateless token upon login, and the client simply sends it back in the authorization header with every subsequent request. But a token with an infinite lifespan is a massive liability. If it is intercepted, it grants permanent access. Tokens require strict expiration limits and rigid validation parameters, checking both the issuer and the audience. Once authenticated, authorization takes over. Looking at this codebase, .NET uses role-based access control. Placing an authorized attribute explicitly requiring the admin role directly over the admin panel action ensures a standard user cannot escalate their privileges to hit secure endpoints. For tighter security, policy-based authorization goes a step further. Panning down to this custom authorized attribute block, developers write granular rules to evaluate custom claims, like age restrictions or specific department ownership, before granting access. Even with all that, an authenticated, fully authorized admin account could still submit a malicious SQL injection. The final, unyielding wall is strict input validation and sanitization on the payload itself. Your database stays secure because you aren't relying on one perimeter wall. You're running a gauntlet of verifications that check the origin, volume, identity, permission, and exact payload of every single request. Let's replay that 3 a.m. attack. The botnet fires its payload. It instantly hits the token bucket limit, fails the CORS pre-flight check, gets denied by the role policy, and dissolves harmlessly against the shield. Junior engineers treat security as a checklist of features to install.
Senior engineers architect their systems around the principle of least privilege, assuming every incoming request is hostile until proven otherwise. Crucially, this system fails silently to the outside world. It securely logs the failed attacks into internal observability tools to analyze the threat model, without ever leaking vulnerable information back to the attacker in error messages. Build your APIs with this architectural mindset, and they will hold the line. Subscribe to the channel for more deep dives into enterprise software engineering.